Alright, we're looking at GSRT Objective 1 still, and this is worksheet 5 that we are looking at in specific. We're going to look at a few things about dilations up close, I guess, in terms of coordinate rules. But before we get there, I want to talk a little bit about the difference between a stretch and a dilation. Now, a stretch refers to basically a non-proportional change. In other words, that maybe we start with a square and then we end up with the rectangular shape. So the height is unchanging, but the width changed. So these are not proportional to each other. Or maybe they both change, but you know, one changes 3 times faster and the other's changing twice. And so again, non-proportional in their change. Okay, we see that with maybe like altering photos and things. So maybe you've got a picture of something, you know, and then you begin to grab it and alter it. Well, if you alter it in particular ways, by pulling it out, you might get, you know, this kind of thing where a distortion kind of is taking place because you've stretched it. On the other hand, a dilation is a proportional change. So a scale factor that affects both dimensions. And you know what this is all about. I mean, it basically takes our shape and we get ourselves a larger version of it, but in the same proportionality. So we can take a look at maybe a couple of pictures here and see if we can determine it. Now, in a coordinate rule, I can tell that this is a stretch because one dimension is being multiplied by 1 and the other's by 3. So one's going to grow and one's going to stay the same. Here we see the same proportionality. This is a dilation. This looks like our height has obviously changed, either shrunk or enlarged, but the other dimension hasn't. Again, that would be a stretch. Here, even though the number is weird, the square root of 5, this is definitely a dilation because both coordinates have handled that in the same value. Here we would see a stretch, and again, for me, if I see a distortion of sort, you know, this did get taller, but this didn't get as wide, you know, or even maybe the width didn't change at all, and then you see a nice dilation here. Now, we want to look at the coordinate rule for dilation, and I think you'll find some of the rule is quite simple. So we're going to dilate from the origin, that's important, and we're going to do a dilation of 2. So I am going to create my ray, and I want to see what happened. My point C at 1 and 3 gets mapped to C prime. And I know how a dilation works. I go up and over, and there I am at 2 and 6. Now I see a very simple relationship happening here. A dilation of 2 is going to take my point, and it's going to map it to 2 of those and 2 of those. Now let's see if that continues here. So let's try a different dilation value. Here we're going to dilate something by 1/2 from the origin. And so again, I draw my ray, and I'm going to do half of that. Now, again, half of the slope, I go down 8 over 2, so half of that would be down 4 over 1, and this point is at 1 and -4. Half of the slope of 6 and 4 would be 3 and down 2. So this would be 3 and -2. So again, let's take a look at the pattern of A prime was at 6, -4. A was. A prime ends up being at 3 and -2. And I see B did the same thing. So I see a dilation pattern here that it would take my point XY and map it to half X, half Y. I don't think I've got another example here, but I don't think we need another one. I think we have our rule, don't we? A dilation about O for a value of K will basically map any XY to KX, KY. Very simple relationship. Boy, we like that. All you do basically is whatever your dilation value is, your scale factor, you just multiply it by the points. So if we were to try and, solve a couple of problems, let's zoom in here on something here. So if I'm going to dilate from the origin to, well, that's easy, -6 and 10. How about this one? 5 times by the origin, 10 and 40. Easy. Let's go down here. How about dilating by -2? Alright, well that would be -24 and +20, right? How about, do we got a fractional? Yeah, let's do this one over here. So a third, so that would leave us at 2, and that would leave us at 8. So very simple rule when we're at the origin. When we're not at the origin, it requires a little more thought, and so be very careful and listen very carefully to how this one works. So here we are, we're going to dilate. Our center is at T, and we are no longer at the origin. So we want to see what the rule is, or how can we work it when we are not dilating from the origin. Now remember, what does a dilation mean? It means a dilation of 2 means 2 slopes. So up 2, rise of 2, run of 1, 2, 3, 4, 5 there. Now if I'm going to dilate again, a scale factor of 2 would mean up 2 and over 5. 1, 2, 3, 4, 5. And I would land at 7 and 8. Okay? And so, again, I have a rise of 2 and a run of 5. Now how do we create some sort of rule to help us understand this? So let me show you kind of what's going on. So we started at -3 and 4. That was our dilation spot. Let me show you kind of what's going on here. Alright, here's how I would like to try and explain this to you. Is that here is where my starting spot is, my center of dilation. And I know that what dilation is really about slope. So if I want to do a dilation of 3, really it means 3 slopes from that starting place. If I want to do 2, I want to do 2 slopes from that starting place. So in this case, I want to do a dilation of 2. So what that means is I'm going to start at my x value and do 2 runs. I'm going to start at my y value and do 2 rises. So let's figure it out. Let's see if we get the same idea, the same answer. My run was 5. And my rise was 2. So I get 10 minus 3 is 7. And I get 4 and 4 is 8. I get the same answer. This is really quite critical understanding that I have a center, and then I'm saying how many of my rises and runs am I going to do. Let's do it again. I know that this is kind of tricky, so keep an eye on it. Here we go again. I'm going to dilate starting at T, a dilation of 1/4 the value. Now, to do 1/4, let's first find our rise and our run. So let's see. We go up 1, 2, 3, 4, 5, 6, 7, 8 is my rise. And then this will be my run, and it'll be negative because I'm going backwards. And I think it's 13, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, it's 12. So here are my values. Now, here's a very critical idea. Even though, like our rise, our slope, as we would say, is a rise of 8 and a run of -12. Typically, in most settings, you would reduce that. We do not want to reduce these numbers at all because they don't represent just slope. They represent actually the slope and the distance to that original spot. So if we want to go 1/4 of that, let me show you how we do it. here's my starting position at 8 and 1. So again, I'm going to start at 8, and then I have a scale factor, and then I'm going to put my run in there. I'm going to start at 1, and I'm going to put my scale factor in there with my rise. Okay, now here's again my starting position, my center of dilation. And if I wanted to do a dilation of 2, 2's would go in here, 3 would go in there, 4 would go in there, and so on. But I want to dilate 1/4. So 1/4 is going to go in there. So almost done. We've got 1/4 of the run. Now the run, do not change this, -12, and 1/4 of the rise, which is 8. And now I can get my final answer. -12 divided by 4 is -3, and 1/4 of 8 is 2, and we get 5 and 3. Now, we could just test that out to see if that actually is 1/4. So that would be 1/4 of this, so that's up 2, and 1/4 of this would be 3 left. 1, 2, 3. This would be 1/4, and this is 5 and 3. Do you see how there are 4 of those in there? Again, there are 4 of those slopes hidden inside of there. Kind of a tricky idea, but if you follow this, you'll be fine.